All right, we're back with our video with the periodic table. So we're going to talk about Dmitry Mendeleev. He was the Russian chemist that basically tackled all the known elements at the time, which there's about 70 that had been isolated and studied at the time in the 1860s. So he was the first person to basically put these ideas together. So before now, we basically had a list of elements. He's the one that basically helped us understand their relationship to each other and put them into a table. His major breakthrough occurred with mass. He realized that the atomic mass, which he didn't know at the time because this was the 1860s, that was actually a weighted average of isotopes because those hadn't been discovered yet. He basically realized that based on their weights, they had a recurring pattern. He realized that every 8 elements tend to have similar properties. So this 8 number is very common in our periodic table. It's our main groups. One of the types of reactions that he ran was testing things in things like water because that was simple back in the 1800s to do. He would take elemental potassium, sodium, and lithium, throw them into water, and realize that lithium kind of buzzed around like a little motorboat producing hydrogen bubbles. We'll see something very similar to that with calcium and acid in one of our experiments coming up, or maybe one that we've already done. And then sodium gets a little bit more vigorous, catches on fire, and then potassium explodes. So it tells us that these elements are similar with their reactivity with water, but also as they get bigger, they get more reactive, and that's because they have more electrons. And when you have more electrons, you care less about losing 1 or 2 of them. In this case, 1 of them. So this law of octaves is this basic idea that there are 8 elements that tend to react similarly in this reoccurring pattern. And the periodic table is full of trends. This just happens to be one of them. So when we think of the periodic table, we say periodic table. It's not just a table of elements, it's a periodic table, and that's because periodically chemistry repeats itself. And in this case, it repeats itself every 8 elements for a while before things get a little bit more complicated. So the law of Mendeleev is this idea that if you look at increasing atomic mass, periodically elements repeat themselves, and that is true. More recently, with the discovery of subatomic particles from our previous video, that's not completely true because there are some isotopes that just randomly happen to have weighted averages that don't fit into this particular law. But it's definitely true that more protons, there is a repeating pattern of 8, and we'll see that with our most modern periodic table. Mendeleev was so talented that he realized that even though elements were missing in his periodic table, that they would be discovered, that they would be known eventually. They just hadn't been discovered yet. So he would take properties of silicon and tin, which are in the same vertical column, vertical group, vertical family, and he'd realize that if the element that was in between was missing, he didn't have to make it up or guess. He knew that the properties above and below would be an average of what would exist for this new particular element. So let's say, for example, that if silicon had a random density of just, say, 4, and tin had a random density of, say, 8, he could guess that this number probably is going to be 6. So using that concept of periodicity, this idea that elements in the same family have the same chemistry as repeated 8 times over with numerous groups of elements or periods of elements coming up, he was able to guess a number like this to be very accurate to the actual discovery years later. So here's how close one example was. He predicted that the melting point of this new undiscovered element, he called X at the time, basically called it ecosilicon because it'd be like silicon, would have a melting point of about 820, and it had a melting point of 930, which was pretty close. He knew its formula would be dioxide, and it would be when it was found in Germany and called germanium years later. The density of his oxide would be 4.7, and he was right on the money there with 4.70. He thought it would be a tetrachloride, and it was. And he thought the boiling point of that chloride would be relatively low, around 100, and it was pretty close at 86. He did this for several elements, not just this one, but he was able to guess these physical properties based on elements within the same family. So well beyond Mendeleev, now we're up to 118 total elements. Again, some of the periodic tables of our textbook are still outdated because it's just been the last few years that some of these have been given names that weren't based on Latin numbers, having those prefixes and so forth. But let's show you parts of the periodic table that are going to be important for some of our homework and exams coming up. First thing to realize is that periods in the periodic table, there are 7. So that's these numbers across the side that are typically not given in most periodic tables. These numbers over here that go across, those are periods, and there's 7. And how that's going to relate to our chapters coming up is in our atom of Bush Stadium, we have this marble and stadium concept. Turns out there are 7 of those. So there's 1, 2, let's use that one as 3, 4, 5, 6, and 7. Those periods just represent the rows of seating, so to speak, in our stadium concept or analogy. Groups are vertical. These are often called families, so we're going to learn several families in the periodic table. I believe it's supplemental 5 in the back of our lab book that helps us individually go through these, so definitely check that video out and complete that exercise later. Most of these have Roman numerals or Arabic numbers 1 through 18. The Roman numerals are going to be very important because these Roman numerals coming up in our next chapter, those Roman numerals can help us recognize valence electrons, which are electrons on the outside. So these are the ones that are most important. Arabic numbers are useful, but once we get to the teens, we're going to have to subtract 10 for those transition metals that we're about to talk about in the middle. So in the modern periodic table, what we have is a group of 2, a group of 10, a group of 8, at least 8 total. So group of 2, that's what I mean 8. Here's the 2, here's the 6, there's the 8 that are most important. When we add those together, we call those the main groups. So 2 plus 6 equals 8. Those are the ones that we're going to focus on in Intro Chem. We are going to see these inner 10 down here for our transition metals. These Roman numerals are important. Notice it's 1, 2, 3, 4, 5, 6, 7, and 8. There's our magic 8. Very important because we can steal valence electrons just by looking up. We're not really going to deal with this part of the periodic table at all. For a lot of what we see in Intro Chem, Gen Chem, you definitely would. So pay attention to those families. This inner section is called the transition metals. Those are the ones that transition between charges, so they're a little bit trickier. So we have to watch out for those. One of the things that this table shows us is the gases. So gases are mostly up in this corner over here, with the exception of hydrogen over there. They're also in red in this particular picture. We also have those liquids that are in blue. Bromine's a liquid here, and mercury's a liquid there. Everybody else is a solid. So if you know the 2 liquids, you know that most of the gases are up in that upper right corner. We'll actually call group 18 the noble gases. It'll be a little bit easier to distinguish, but that's also available to you in the big periodic table in our classroom if you're in the face-to-face class. We also have a couple families underneath. We have our lanthanides and actinides. So after lanthanum, notice we drop down, and those are the lanthanides. And then we have actinium, we drop down, and those are the actinides. So it is kind of weird that we go from 57 to drop down 58 through 71, and then back up to 72. The reason we do this is because that's a different section, a different sub-level, so to speak, that we'll talk about in our next chapter. But stadiums have lots of sections. We basically have a section here. We'll call this S. We'll call this section P, this one D, this one F. So there's a reason for it. We'll just cover it in our next chapter. But also, if you think about it, if we were to extend this 14 more elements across, now our periodic table would be 10 foot long, and we'd fit it on the we'd never be able to fit it on any cover of any textbook ever. So for a couple reasons, we've kind of shrank it and threw it out underneath to make it a little bit more viewable on most standard pages. So again, the main groups are our focus. It's the first 2 to the last 6 to make 8 total. Transition metals recognize those enter 10, and then the lanthanides, actinides are in that lower section, not given numbers. We do want to pay attention to the Roman numerals. Those are going to help us with valence electrons. One of the first and most important families of the periodic table is the noble gases. Everybody wants to be like them because they are full. So it's kind of like if you're a rock star or superstar, you want your stadium to be full. You want to be sold out, so to speak. And this is exactly the case for the noble gases. They're the kings and the queens of the periodic table. They want their kingdoms to be full. They want their electrons and their inner levels to be full, with no extra electrons, no missing electrons. So what other elements do is they're going to gain or lose electrons. And if you lose electrons, this is what's hard for students to remember. If you lose electrons, you're going to be positive because your protons are still there. If you gain negative electrons, you're going to be negative, and that's because now you have more negative than the protons that were always there. So be careful with those 2 definitions. Those are things that students oftentimes get backwards. The noble gases, group 18. We see that as our most prominent and now in our gray boxes here on the end. So your noble gases are on the edge. One thing I like to do in the periodic table is separate it based on the metalloid line. It's usually a dark black line, so here it's in red, but it's basically this little staircase that kind of zigzags down through here. So again, this little staircase separates things from metals and nonmetals. So basically over here we have all of our nonmetals. And then over here, with the exception of hydrogen that's still with its nonmetal friends, all of these are metals. So by knowing those 7 in green, we can know everybody that we need to know based on left and right, with the exception of hydrogen. So watch out for these guys here. These ones in kind of that green color, those 7 are both metal and non-metal in their properties. So a lot of them used in computers and TVs and so forth. So what makes them different? Metals tend to be shiny, non-metals tend to be dull. Most of them aren't even solids, they're gases. Most metals are bendable and malleable, or even ductile, which means you could pull them into a wire. Most non-metals would break. Most non-metals aren't even solids that could break. Most metals conduct heat and electricity. Most non-metals conduct electricity, but again, most of them aren't even solids that could have that ability. And then metalloids have the best of both worlds. They have kind of intermediate products, so-called metalloids or semi-metals in some textbooks. What are the main groups? Again, that's the first 2, the last 6, total of 8. And then what do these families have in common? They have similar chemical properties, meaning they'll have similar charges because they have similar stadiums on the outside of their electrons. As we look at other families, know that alkali metals and alkaline earth metals, they're different by the number of words in their names. So for example, alkali is 1 word and it's in group 1. Alkaline earth is 2 words and it's in group 2. That was the easy way for me to remember it back when I learned them. Where I learned about the noble gases, those are group 18. That's the kings and queens of the periodic table. The halogens and chalcogens, notice the spelling of both of these is very similar, but chalcogens is closer to C. Halogens is further away, so maybe that helps understand the difference between the two when you're asked about them in the homework later. Here's a little bit of practice. We're going to practice this on a periodic table that we're given in class. So alkali metal 4th period, halogen 3rd period, and so forth. Let's try. All right, so let's go through letter A. Alkali metal of the 4th period. Alkali metal of the 4th period. So, first things first, let's find the alkali metals. Alkali metals are group 1. And then it says 4th period, so we're going to go down 1, 2, 3, 4 periods and find potassium. And that's letter A. Let's try a halogen from the third period. So halogens are in this group 17. And then they say go down 3 periods. So first period, second period, third period gives us chlorine. So be careful. Notice on this one, we use this as the first period because it is. Just because there's not an element there doesn't mean we don't count it. Let's try another one. So again, chlorine being our halogen of the third period. Let's try letter C. Alkaline earth metal, 6 period. So alkaline earth metal is group 2. 6 period means 1, 2, 3, 4, 5, 6, go all the way down to barium. So again, like the halogen example, notice we are using this. This is period 1. We just don't have an element there. So don't forget that we are going down 1 to 2 to 3 to 4 to 5 to eventually 6. Letter D says noble gas of the fourth period. Let's find that one. So noble gases, group 18, magic number 8. And then it says go down 4 periods, so go down 1, 2, 3, bingo is 4. Krypton, the answer there. Next it says metal of group 7. Group 7, period 4. So here's group 7, the literal number, group 7. And then it says period 4. Well, 1, 2, 3, 4 is your period. That's the first element of the actual group 7. So manganese. Then we have semi-metal in letter F. Semi-metal or metalloid of group 3. So let's find group 3. This is group 3 specifically, but what they're after here is actually group 13 because that's Roman numeral 3, and it's the only semi-metal of that family, which happens to be boron. So a little tricky there because they were after the Roman numeral, not the actual group 13 as listed in the actual question. Then we have actinide. Actinide just means find actinium. So once you find actinium, after 89 becomes 90. Then they say go to the highest atomic mass. The highest atomic mass here would be the biggest, which is 262 lawrencium. Lastly, we have a rare earth metal with the highest atomic number. So rare earth metals we did not mention exclusively, although they were mentioned in the notes briefly. I just didn't touch on them until now. The rare earth metals are basically group 3, so this section of the periodic table. And then it also includes the entire lanthanides all the way across. Those guys count too. So when they say, in this situation, who has the highest atomic number, it would be the one at the end. So lutetium. So as we look at these answers, pay attention to periods. Periods go kind of east and west. They go left and right. Those are horizontal. Pay attention to groups. Those go vertical, kind of north and south. Those are the ones that typically have family names. Those have Roman numerals that you have to distinguish from the numerical numbers and so forth. So as we start to learn more about these particular families and groups, realize that we're going to understand why they have this kind of broken up appearance in these four kind of tall skinny blocks or long rectangular blocks or square blocks or so forth of the periodic table, and that's what we're going to see with our electrons in week 3 coming up. In a separate video, we'll start to cover ions, which is one of the more difficult concepts of this chapter.